let's see. And then I will start the recording and we can just go.
Fantastic.
So we probably have to do the introduction again. Okay, great. All right, we're live. All right, so hello again. So today I'm hosting this week's seminar. My name is Philip Weinberg. I'm Adrian's postdoc. Adrian can't be here because he's on vacation this week, but today we have the pleasure of Andrei Bernevig giving us a talk on quantum many-body scars. And without further ado, Andrei, how about you go ahead and give your talk?
Thank you so much. Thanks for having me over virtually. And is this live? Is this going live on the internet?
It is, yep.
Oh, wow. It's amazing technology. Hello, internet. And is there a way to not hear when people like...
Oh, come in. Yeah, let me try that. Let's see.
I guess you hear when people leave too, which might be more of a problem towards the middle of the talk.
I think I just changed this setting now. It should be working.
Oh, great. Thank you, Christia.
No worries.
Okay. Fantastic. So yes, so thank you, Philip, for hosting this, and Adrian for inviting me. Adrian, I hope your vacation is going okay. So I'm going to talk today about something that we are excited about because it's the first example of writing down exact many-body states in the middle of the spectrum of a non-integrable model, and it's basically it's a direct counterexample to the strong ETH principle. It's a direct counterexample that's exact, which cannot be argued away because of numeric sizes. So basically, I'm not going to be talking about the motivation very much of the work, but because we didn't get to it motivated by experiments. But then a couple of months after our work and independently, there were explanations of cold atom experiments that basically had to do with exactly the same phenomenon that I'm going to describe here. But basically, in general, I want to point out that cold atom experiments are enabling the study of non-equilibrium dynamics of interacting quantum systems. So it's not very far-fetched that most of the things that I'll describe here can actually be someday experimentally realized, and some of them have already been experimentally realized in Rydberg atom systems. So what I wanted to basically talk about are several things. I wanted to first review some known facts about quantum systems and ergodicity in quantum systems, and then I wanted to point out the first example of ETH violation, which happens in a spin 1 AKLT Hamiltonian, and going from there, basically a set of wide-ranging connections to matrix product states, Hubbard models, fermionic models where these things happen, and other systems. Okay, so for the purpose of today's talk, what I'll be talking about mostly are the mid-spectrum of many-body systems, so the finite energy density spectrum of the many-body systems, and I'll be mostly focusing on computing a quantity which is called von Neumann entropy, which basically has to do with the fact that you take a system, you form its density matrix, then you take a part of the system, separate the system into two parts, A and B, you trace out the density matrix, form the reduced density matrix, and then you compute its entanglement entropy. And if the system is, for example, non-integrable and not many-body localized, as I'll explain later, it is basically thought that this entanglement entropy has a set of rules for states in the middle of the spectrum or states at finite energy density. And this set of rules will be given in the next slide, but basically they come from realizing or from postulating really that the reduced density matrix of a state in the middle of the spectrum, which here we'll call them thermal states, is actually equal to the Gibbs density matrix of this subsystem for a local Hamiltonian. And this type of postulate is called the Eigenstates normalization hypothesis. And basically, I'm not going to be able to go through all the predictions of this, but one of the predictions of the Eigenstates normalization hypothesis is that the states in the middle of the spectrum, the eigenstates in the middle of the spectrum, are thermal, and hence their entanglement entropy obeys a volume law. So if I look at the spectrum, which I'm not sure if you're seeing my mouse, but I think you are. If I look at the spectrum of a many-body system, forgetting about quantum numbers, the spectrum looks something like this as a ground state. It of course has a highest excited state which you can make the ground state by just negating the Hamiltonian, and then it has a rather sparse low energy spectrum, which are called ground state-like states, and a sparse very high energy spectrum, which I'll also call ground state-like states, because if I negate the Hamiltonian, they just become these states. And then they have a very, very exponentially dense spectrum, which is the region where this Eigenstates normalization hypothesis should happen. And this is the spectrum of states that are postulated by the ETH to be thermal states. So ETH would say, for strong ETH, one of the consequences would say that if I pick any state here, then take the state, take the space on which the state lives, which is the real space for a hopping Hamiltonian or for a spin Hamiltonian, cut the space in half, form the reduced density matrix of this state, trace out half of the system, then form the entanglement entropy. The entanglement entropy will scale as the volume of the system. And this really has to do with the fact that, for high enough states in the spectrum, basically correlations happen all across the system. So the strong ETH basically says that all eigenstates at finite energy density satisfy the Eigenstates normalization hypothesis. So any state that I would pick here, or here, or here would have an entanglement entropy which would scale as the volume. These states, the ground state, have entanglement entropy that scales as the area, which is the famous area law. And actually, you can prove by matrix product state techniques that the ground state-like excitation, so the sparse part of the spectrum here, or these states here, obey also an area law, just like the ground state, with entanglement spectrum that's actually related to the ground status. We'll talk about it later. But basically, it's thought that Hamiltonians without many extensive conserved quantities obey this strong ETH. And we know of two types of ETH violation, which are integrable models and many-body localized models. So many-body localized models, eigenstates that are in the middle of the spectrum, for example, can have area law, and integrable models as well. But these are models, the integrable models are models with a extensive number of conserved quantities, and many-body localized models are basically thought to be sort of integrable-like. It's, some people call them, I guess, stable integrability. It is thought to have a large number of conserved quantities as well that are stable to actually even smaller perturbations. So these are the two examples of ETH violation, and it was thought that if you don't have either integrability or many-body localization, or both them, then the spectrum will satisfy the strong ETH. So I want to point out that basically through a set of exact examples that there's a third possibility, and the third possibility is that there are states in this in the middle of the spectrum, here represented by a set of equidistant energy states that can have subvolume, even actually sub-area in our case, can then have subvolume entanglement entropy, and these states will violate ETH, and in hindsight they're now called scarce states. Now there could be more than, in this case there's a polynomial number of states in the volume of the sample that violate this ETH, but I could have actually an exponential number of them, or a sub-polynomial number, a finite number of them. So the possibilities are multiple, but there are systems where ETH is violated, and we'll give an exact example of this. So the reason why these states are called scarce is because people have made classical analogs of these. Early on, I guess in the 80s, people have made classical analogs of the breaking of chaotic behavior. For example, in billiard balls, where you have, depending on some angles, you have some trajectories which are more populated than the others, and the name comes from actually being borrowed from the classical literature. Okay, so what are the outstanding questions, and what was preventing people from actually proving ETH? Well, proving ETH is a very tricky business, because, and that's why it's still actually a postulate, because it involves states in the middle of the spectrum. And states in the middle of the spectrum are very, very hard to solve. And in fact, with the exception of a few integrable models, it's not known how to solve for any eigenstate in the middle of the spectrum. For integrable models, it's, we have techniques such as Bayesians, etc., other techniques for which you can solve for states in the middle of the spectrum. But if you are given a non-integrable model, even if you can solve for the ground state, it was not known how to solve for states in the middle of the spectrum. I would claim that we still don't have a full understanding of which models, would have states in the, would have exactly solvable states at finite energy density, where the spectrum is exponential. So hence all the ETH and all the, in fact, a lot of the many-body localization literature is basically a series of very smart conjectures supported by large-scale numerical calculations. And these calculations are, of course, subject to scaling, and hence it's beneficial to actually find an example that's exact, where you can prove or disprove things without resorting to numerics. So what we were able to find, and what I'll present today, is a set of a tower of states, which basically interpolates between the ground state and the highest excited state. So it has to go through a region of high density, energy density, exponential density of levels in a non-integrable models that you can solve for exactly. And being able to solve for exactly, you're able to solve for the entanglement entropy. And being able to solve for the entanglement entropy gives you an entanglement entropy that's not, that doesn't satisfy ETH, that's not the volume law in the middle of the spectrum. Hence, these provide the first analytic example of ETH violation. So the model that we used is a very well-known and simple model. It's the spin-1 AKLT model, and I'm just going to go through it very quickly. It's actually a sum of nearest neighbor projectors. So you take, it's a spin-1 Hamiltonian with spin-1s sitting on every side, and you take two spin-1s and you project the nearest neighbor two spin-1s into a total a spin-2. Hence, if my ground state actually would be the zero energy state that doesn't have any component of two ADS and spin-1s on the spin-2, and you can write its form in spin operators, and it's written here. And this Hamiltonian has been used, of course, to actually prove that Haldane gap exists in a model, and it's also the prototype for symmetry protected topological phases, matrix product state wave function. So it's kind of a very, very good Hamiltonian to use to teach, you know, the, I guess, beginning graduate class about, you know, Haldane gaps, symmetry protected topological states, matrix product state wave function, because it's got a very simple ground state. In fact, we can just write the ground state in a way that I'll continue using as a representation. What you do is, for every site where you have a spin 1, you think of the spin 1 as 2 spin 1/2 degrees of freedom, which are symmetrized. So 2 spin 1/2, which are represented here by the small dots, form a spin 1 represented by the big dots. If I symmetrize them, they're just, you know, I lose the singlet, I just symmetrize them. And in this Schwinger boson representation, I make a singlet between 2 spin 1/2 bosons, so 2 small circles on adjacent sites, by drawing a dimerized line. So this actually represents, this is spin 1/2, represents spin 1/2 here, spin minus 1/2 here, minus spin minus 1/2 here, spin 1/2 here. This is this representation. And now you can see that if I form a singlet between 2 adjacent sites, then this spin 1/2s are in a singlet. So the only thing I have left over is a spin 1/2 here and a spin 1/2 here. And they can be in a singlet or a triplet state. They can be in s equals 0 or s equals 1 state, but can never be in s equal 2 state. So by forming a singlet between these 2 spin 1/2s, I've basically guaranteed the projection property of the Hamiltonian that 2 adjacent sites can never be into a spin 2, because I only have 2 spin 1/2s remaining. Their sum can only be 0 or 1 spin 1. These 2 sites, if I form a singlet between them, can never be into a spin 2, and hence basically this is saying that if I act with the projector, which is the Hamiltonian with the sum of these projectors on this singlet between 2 sites, I get 0. Okay, and this allows me to write the ground state exactly, and this is the ground state. The ground state is just a dimerized form of these spin 1/2s, and of course now you can see the symmetry protected topological state. If I cut the system, for example, if I cut it here, I'll remain with 1 spin, which spin 1/2, which is unpaired. So I fractionalize the spin 1, which existed here, into a spin 1/2, which is now the edge state. So you can clearly see, you know, both the fact that I can have an exact ground state of this system, which is this state. Of course, the ferromagnetic state is also exact because of the other property that if I project with this operator on the spin 2 state, I just get the spin 2 state because the projection to spin 2. So the highest excited state and the lowest excited state are exactly solvable. And please interrupt me if there's any questions at any time. Exactly solvable. And you can also see immediately from the ground state the fact that it's a symmetry protected topological state, because I have an edge state. If I cut the system here, I have a free spin 1/2, which is just this guy here, which basically is a fractionalized spin 1. Where I fractionalize the spin 1 is 2 spin 1/2s, and I moved one of them to one end of the sample, the other one to the other end of the sample. The fact that it has an exact ground state does not mean that the whole system is integrable. And in fact, the system is not integrable. There's many systems where you can solve the ground state exactly, but that are not integrable, Junda-Gauss being another one. So for example, here we show the energy, the level repulsion of this system of the AKLT chain, and you can see a clear Wigner-Dyson in the orthogonal ensemble. The Hamiltonian is real. In the orthogonal ensemble class, which basically tells you the system is not integrable. If it was integrable, the level statistics of the eigenstates of the system would follow Poisson distribution. So this system is not integrable. It certainly isn't many-body localized because it's translationally invariant. I haven't added any disorder. It's also, it also doesn't have many-body localized systems with see Poisson distributions also. So it's one of these models where I could probe further whether I have interesting behavior because it's not integrable and it's not many-value localized. I just want to point out that it's part of a set, that this model is a part of a set of many other models which have exact ground states. These are all projector Hamiltonians. For example, the Haldane pseudopotentials of the quantum Hall effect have exact ground states. The Shastri-Sutherland model has exact ground states. Majumdar-Ghosh models have exact ground states, and they're non-integrable. In fact, a lot of these, projector Hamiltonians are non-integrable. There's some projector Hamiltonians that are integrable, like stabilizer codes, but most of them are not. Well, a lot of them are not. Okay, so now I know the ground state of this model. This was known, since the work of AKLT. But the question that we want to ask is, are there any other states in the spectrum that are interesting? And the zeroth order thing that we did is to diagonalize this model for a large size of 16 sites. So, Hilbert space 3 to the 16 plus symmetries. And what we found, to our surprise, by looking at the spectrum, by hunting, you just take, well, for 3 to the 16, it's kind of hard to just look at the spectrum. But what you do is, you start with smaller sizes, you see some patterns, and then you go to the 3 to the 16, and you get the spectrum with machine precision, and then you ask, are there any energies in the spectrum that are actually integers? And remarkably, you find out a tower of states at these energies. These are the energies of some states in the spectrum, which I'll call them, the states that we're interested in are these S states. Okay, so we'll call them scarce states. There's some states in the spectrum at integer energy. So basically, the moment you see that there's some integer energy in this game, you've found something that you should probe further, because if I have a 3 times 10 to the 3 to the 16 times 3 to the 16 matrix, and I try to diagonalize it, there's basically zero chance that if this matrix is random, or if this matrix doesn't have any further structure, that I'll obtain eigenvalues which are integer or rational, which are basically for this purpose also integer. Moreover, what we found that was interesting and that made us probe further into these structure of these eigenstates is that if you go to, if you start with L equals, let's say 6, and you go to L equals 8, and you go to L equals 10, etc., the energies do not change. So this is not a finite size effect. For example, if I have small L, if I have L equals to 2, I could get integers just because I have a small matrix of integers, and maybe somehow the eigenvalues are integer. But if these eigenvalues don't change and remain the same as I go to larger sizes, then there's got to be something special about the eigenstates of these eigenvalues. And moreover, of course, as you go to larger sizes, you get more and more. So for if I went to L equals 18, I would get a state at energy 16, etc. The other thing that you find is that you can target these states by using another method. What you do is you diagonalize for this AKLT model, and you look at the entanglement spectrum of every state in the system. So here it would be 3 to the 16 states. You look for you calculate their entanglement spectrum, which is just the reduced density matrix, the eigenvalues of the reduced density matrix, and you ask, what is the rank of this matrix? And normally, if for each state, and normally I should get if it's for a generic model, I should get that the rank saturates the Hilbert space dimension. But for these states here, the rank, the reduced density matrix, has actually very, very small ranks. So they're special in the sense that only certain configurations are favored, and the other ones in these states, and the other ones have amplitude 0. I don't mean 10 to the minus 7. I mean really 0 to machine precision. Okay, so today what I wanted to talk about is this set of states, and in the AKLT model, and then move to fermionic, to the Hubbard model, to show you that the set of states exists there too. So I want to point out that we can obtain expression, a very easy expression for all these set of states, and calculate the entanglement entropy and show that they violate the eigenstate normalization hypothesis. As you see, they interpolate between the ground state, which is energy 0, and the ferromagnetic state. Okay, this is the value of their energy, and hence by showing that all of them, all these states violate ETH, it means that strong ETH can be violated in the middle of the spectrum without integrability and without many-body localization. Okay, so let me give you the expression for these states. It's very easy to get. You get the ground state, and I remember I remind you the ground state, the AKLT model is just a series of 1/2 singlets of spin 1/2 singlets between two sites. So it's basically a dimerized version. And what I do is I take what we do in this paper is we take the ground state and we hit it with the spin raising operator squared on site n. This creates a spin 2 magnon because this is a spin 1 and squared is spin 2. And what it does is it acts only on the site n, polarizes the spins on site n. This is a spin 1. And of course, to get a spin 2, you know this has to be a spin 2. You are going to polarize the spins on site n-1 and n+1, the spins 1/2 of the singlet. So you basically broke these two bonds. The only action that it does is it broke these two bonds, and it picked up only the up configuration of, this is 4 spin 1/2 to spin 2 state. That's the only thing it does. So now you ask, how does the Hamiltonian act on this state? Well, that's very easy to do because I remind you the Hamiltonians are some of these projectors. The projectors on every spin singlet are 0. So that means that the action of the Hamiltonian on this state, which is just a very small deviation from the ground state on site n, is very simple because I don't have to worry about anything to the left of this and anything to the right of this. The Hamiltonian will still give me 0 on this. I only have to worry about two terms, the Hamiltonian acting on these two sides and the Hamiltonian acting on these two sides. And indeed, the Hamiltonian scatters the state only to two configurations, as it should. One configuration is this one, and one configuration is this one. So just this is obtained by acting the Hamiltonian on these two sides. The Hamiltonian is a projector between two sides, and this is obtained by acting the Hamiltonian on these two sides. So you also now notice that if I call this state n, this state is just a translation of this state by one lattice constant. So the Hamiltonian, when it hits the spin 2 configuration on site n above the ground state, which we call mn, this one, scatters to two states. So this is the scattering equation. Scatters to two states. This is one of them, n-1, and this is the other one. So now it becomes clear that if I form the momentum pi combination of the spin 2, so if I take this to a spin 2, there's going to be, at momentum pi, there's going to be a minus sign between these n configurations, big N configurations between two. They will cancel. So the momentum pi configuration, which I take by implementing a -1 to the power n on the spin 2 above the ground state, is an eigenstate of the Hamiltonian at energy exactly 2. So we found the first eigenstate. It's the the momentum pi configuration of the spin 2 magnon above the ground state, and this is this state. And remarkably, what you find is that the series now continues. So let me call this operator, spin 2 at momentum pi, I'll call it P operator. The ground state is just the singlets. The first state is just P on the ground state. The energy 4 state is P squared on the ground state, and I keep flipping spins until I get to the ferromagnetic state, which is P L/2 on the ground state. So all of these are eigenstates of the Hamiltonian, and they're exactly this tower of eigenstates. So the red tower of eigenstates coming from the ground state, going into the ferromagnetic state here, they are the exact ground state. We have an expression for these other, the states in black here. We have an expression for them, but these are states that are very close to the ground state or very close to the ferromagnetic state, and I won't go into them further because they don't prove anything about the ETH being that they're close to the ground state or the ferromagnetic state. Okay, so now having these states analytically, we can compute their entanglement entropy. So what we do is we write each of these exact states as a matrix product states, and it turns out that you can write them down as a small bond dimension. The reason for this is that the ground state, written as a matrix product state, is a bond dimension 2 state. And then this is a local operator. It's a spin 2 operator on site. And local operators acting on a small bond dimension cannot create a large bond dimension matrix product state. And it turns out that we can write each of these states as a matrix product state with bond dimension 2 times n minus 1. So the state at S2n is 2 times n minus 1. And hence you can bound the entanglement entropy of each of these states exactly. It's bounded by logarithm of 2 times n plus 1 n goes between 0. This would be for n equals 0 would be the ground state. For n equals the length of the system over 2, this would be the ferromagnetic state. So this n, if it's in the middle of the spectrum, is proportional to the size of the system. So you can clearly see that the entanglement entropy of these states is bounded by logarithm of the length of the system, which is very different from S being proportional to the volume of the system, which was predicted by ETH as being true for any state in the middle of a non-integrable system. Moreover, you can see just plotting the entanglement entropy of every state at, for example, 16 sites. This is the energy of every state in the AKLT system. This is the entanglement entropy. Okay, and non-integrable systems would have basically this semicircle law here. But without these drops, these x's. So a non-integrable system would have a generic one. Now, a non-integrable system with a set of ETH violating states in the spectrum will basically show, just like plotted here for the AKLT model, will show a series of states where the entanglement entropy is much lower than what it should be. So this is what it should be from the ETH prediction, for example. But you can see that there are these series of states that basically scar the spectrum, the entanglement entropy spectrum, and they have much lower entanglement entropy than, for example, the volume. This would be volume law, and this would be the log volume states that I showed you before. So this is the band of outliers. They're all these states that we can obtain exactly, and with entanglement entropy we can bound exactly. Okay, so before I go to the next topic, which is also related to this, but sort of changes pace a little bit, I just wanted to ask if there's any questions left. Is there any questions? Not left, but any questions?
Yeah, so if you have any questions, just raise your hand and I can unmute you, or otherwise you can type them into the chat and we can read them at the end. So we have a couple of questions in the chat. Do you want me to read them, or do you want to just continue?
I think if you can judge if they're better now or at the end, it's your call.
So this one doesn't seem like it's a clarifying question. So Yeah, maybe we can limit it to clarifying questions for the meantime.
And you can read the ones. Okay, good.
Yeah, so I'm going to say let's probably just continue, and then we can just go and do all the questions at the end.
Okay. So what I wanted to point out is that so I'm not going to go through this in detail, but what I want to point out is that we now understand how to construct at least a series of Hamiltonians that have these type of scar states. So the question was always, are these scar states only happening in the AKLT model? And the answer is no. As I'll show in a little bit, they happen, models that are not exact. Also, you can obtain them numerically, but there is a way to construct a large class of models that are non-integrable and that have these type of scar states in the middle of the spectrum with low entanglement entropy. And there's a prescription of obtaining them through basically brute force creating them. So you first create a frustration-free Hamiltonian. You pick a ground state, which is a matrix product state. If this matrix product state is injective, people in the matrix product field have figured out how to obtain a Hamiltonian, which this ground state is a frustration-free Hamiltonian, which this ground state is the exact ground state. And then you can take that formalism and extend it to forming quasi-particles. So basically, I don't have time to go through this, but there's a very clear way of finding if a ground state represented by a matrix product state, if a state represented by a matrix product state can be the ground state of a frustration-free Hamiltonian, and if the answer to that is yes, there's an easy and clear way to determine whether that Hamiltonian or whether that set of Hamiltonians, because it's usually a set of Hamiltonians depending on some parameters, can have excited states, which are also exact states, which are given by this operator B, which you act on the ground state. The B was the spin 2 operator that I showed before. So you can find the operator B for which you can have a tower of states, and there's some conditions basically that you have to impose, and these are a series of conditions that you have to impose on this operator that I don't have time to go through. But basically this, for example, leads us to a most general Hamiltonian, nearest neighbor Hamiltonian, which has the exact same scars, or the exact same eigenstates as the AKLT state. So this is at the AKLT scars. So I gave you a set of eigenstates which are coming from the AKLT model, but it turns out that first there's a series of Hamiltonians that have those states as eigenstates in the middle of the spectrum, and this is the expression of these Hamiltonians, a whole manifold of them. So these are projections into nearest neighbor Hamiltonians, nearest neighbor spins of spin 2 and S equals to 1, as spin 2 and S equals to 2, etc. of adjacent sites. And this parameters, the ZJ, MN, are some complex numbers that you can tune subject to hermiticity constraint. But basically you have a large set of nearest neighbor Hamiltonians with eigenstates in the middle of the spectrum that are, for example, identical to the AKLT ones. Then you can also change the AKLT ground state, okay? And I can, for example, form here. I'm giving another matrix product state. This is for the people that are familiar with matrix product states. This is another matrix product state that tells you that the matrix product for spin 1 is some constant C plus times sigma plus. The matrix product for spin 0 on site is some other constant times sigma Z, and the matrix product for spin -1 is C minus times sigma minus. This will give you a state which is different from the AKLT state, depending on these C pluses and C minuses and C0. But you can also find that a Hamiltonian for which this is the ground state, and then you can find that the same raising operator, the same spin 2 at momentum pi, okay, on this ground state, which is distinct from AKLT, forms a set of scarce states. And you can find the Hamiltonians, for which these are scarce states, and there's a continuous family of spin 1 scarce Hamiltonians connecting the AKLT to the integrable pure biquadratic point. So for example, this is the set of Hamiltonians that have scars, which are exactly defined by the same operator as the AKLT operator, but they're distinct because the lowest ground state on which you apply this operator is different. So there's a set of scars for all these Hamiltonians, for example. And this method, this matrix product state method, can be used to construct other Hamiltonians, and hopefully can be generalized to multi-site Hamiltonians. So far, we have a method only for nearest neighbor Hamiltonians, but hopefully it can be generalized for other Hamiltonians. Okay, so what I wanted to end with is to show you that this is not a peculiarity of spin systems. So I want to show you that there exist scars in fermionic systems, and specifically in two-dimensional fermionic systems, for example, actually in any dimensions in this case, but in two-dimensional systems. And the most famous two-dimensional system that's fermionic is probably the Hubbard model. And the Hubbard model is, of course, just spin up and down on a site, on a series of sites, which we'll call here a graph, because we'll extend the Hubbard model to some. It's probably a useless extension for reality, but in any case it works. Plus a up-down Coulomb term on site. So Young, basically C.N. Young, showed that this Hamiltonian, in some conditions of, for example, nearest neighbor hopping, or neighbors actually odd neighbor hopping, it turns out, has not only a spin symmetry, which is an SU2 spin symmetry, but it has another symmetry which is called eta pairing symmetry. And this eta pairing symmetry is another SU2, which we'll call the pseudo-spin symmetry, is a charge 2 operator, unlike the spin, which is a charge 0 operator. So it's basically like a superconducting symmetry. It generates states with some pairing. That's why they call them eta pairing. And what you realize is that, in fact, this state commutes with a Hubbard Hamiltonian up to itself. And these are very nice. So, if this was 0, this would be an actual symmetry. But this is a spectrum generating algebra, because it tells you that if I have a state if I have any state of the Hamiltonian, I hit it with eta pairing, and I form another state at energy, that of the previous state, plus U minus 2 twice times the chemical potential. At twice times chemical potential exactly equals to U, this is an exact symmetry. Otherwise, it's a spectrum generating algebra, which is as powerful as a symmetry. So let's call it a full SU2 pseudo-spin symmetry. So that's why people say that the Hubbard model usually has an SO4 symmetry. It's SU2 cross SU2. It's generated by this eta pairing operator. So far it's a symmetry, and this, as I said, the fact that it is a spectrum generating algebra, so it commutes with a Hamiltonian up to itself, then this means that it can generate a tower of eigenstates with spacing epsilon starting from any eigenstate psi 0 of the Hubbard Hamiltonian. Now this starts to sound familiar, but why aren't these scars? Well, they're not scars basically because this is already a symmetry. And if I was to break the Hubbard spectrum into symmetry sectors, then these eta pairing states would be actually the only states in their symmetry sector, and hence the level spacing there, you wouldn't have any non-trivial level spacing. So these are not yet scars, because scars are something that doesn't come from a symmetry. It's not. It's the operator, the momentum pi spin 2 operator in the AKLT state is not a symmetry, for example. And in order to obtain scars, I have to do something to get rid of the symmetry. But first, let me the eta pairing symmetry. So first, let me show you that basically the Haber model has a lot of exactly solvable states. So for example, any state that has only spin up on the ground state, on the vacuum, is an eigenstate of the Haber model. The interaction doesn't act. You just fill up the Fermi C here, or you just not, it doesn't even need to be a Fermi C. It can be scatter momenta. You just add up the energy of the single particle energy. This is an eigenstate of the Haber model. Now I act with this eta pairing on this state. I form some, some charge 2 operators here on this momentum configuration. Here is any momentum configuration, by the way. And that's an eigenstate of the Haber model also. Okay. So now the question that we wanted to ask is, can we add terms to the Haber model that break this eta pairing symmetry? So break the fact that you have, the eta pairing commute with the Haber Hamiltonian up to itself. Okay. But hence you don't have this type of situation that any state that you start off with, you just act the eta pairing operator and you obtain another state in the spectrum. So you break the symmetry, but there is still some set of states that interpolates between the ground state and the highest excited states that are exactly solvable. And the answer is yes. And I don't have time to go through the full derivation, but the general idea is that you have to relax the spectrum generating algebra condition to a spectrum generating algebra that acts only on one state. So we claim that if you start off with a state that's an eigenstate of the Haber model. So for example, think of psi 0 as the vacuum state, just the unoccupied state. Certainly it's an eigenstate of the Haber model. Then if the commutator of the Haber model and this eta pairing operator is no longer equal to some energy times the eta pairing operator, but is equal to the energy times the eta pairing operator only when acting on phi 0. So you see, normally a spectrum generating algebra would be this equation, but with phi 0 removed from here. So it would be the same, the commutator of H and eta dagger would be epsilon times eta dagger, no matter on which state you're acting. But I can then restrict the spectrum generating algebra to ask that this commutator is true only when acting on one state. So if these two conditions are true, and furthermore, the second order commutator cancels for every state, then I have a tower of states. Then the tower of states where I act eta dagger to the nth power on this state psi 0 is all of these are eigenstates of Hamiltonian. These are my scar states. So this, we'll call it the spectrum generating algebra of order 1, and will become clear why it's order 1. But in any case, the moral of the story is that if these conditions are satisfied, where you relax the spectrum generating algebra to being true and acting only on the state psi 0, and the second commutator vanishes here, then these states are a set of scars, a set of exact eigenstates of the Haber model. So it turns out that it's easy to find. So the question that we asked is, can we add some terms to the Haber model such that they break the fact that eta dagger is a spectrum generating algebra, but they still satisfy it when I act both the left and the right hand side of this equation on some state. And it actually turns out that it's very easy to find these things. For example, if psi 0 is the vacuum, such a Hamiltonian, okay, with this condition, okay, would make the eta pairing not be a spectrum generating algebra, but would still keep the eta pairing being a spectrum generating algebra only when acting on the vacuum. And there's other models that were constructed that basically fall into the same structure. And then, you can generalize this. So this is basically, you see, this is kind of like a Lie algebra that stops at one point for this. So basically, you can generalize this to order m scars. If I have a state psi 0, then eta dagger acting on psi 0, eta dagger to the power n, to any power acting on psi 0 will be an eigenstate of the Hamiltonian if I have the following conditions. So, for example, the Hamiltonian, the psi 0 is eigenstate of the Hamiltonian. The spectrum generating algebra works only when acting on psi 0. All the commutators up to n times work when I act on psi 0, and the commutators above some value m always work. So basically, there's all these conditions that you can do, that you can generalize these scar states. So I think I'm mostly done, but I wanted to basically point out that actually, parallel to this, so while we were doing the AKLT, we didn't know anything about the experiments. There's Rydberg atoms experiments, which are modeled by this PXP model. And completely parallel to this, I guess, people like Abanin, Slatko Papic, and Mishalukin and other people were basically trying to model the behavior of Rydberg atoms in cold atoms, and they were seeing some revivals. And they basically, there's in this theory paper that this was completely independent of our work and showed up, I think, a couple of months after our work. None of us knew about the others. They basically showed the same type of behavior numerically in this PXP model. You can see the entanglement entropy with these scar states going down. Now, the scar states in this model that's supposed to that not only supposed but does model the Rydberg atom experiment. The scars in this model are not exact, so there's many people cited here trying to make them exact, and you can get very close to being exact, I guess exponentially close. I can never get to being the exact scars, but by doing numerics, even on on the sizes available, you can clearly see the same type of scar behavior. So I wanted to basically point out that now there's many understandings of these scars, both in the PXP model from the group of Zlatko Papic and Dima Abanin and Serbin, and from other groups like Yadakola et al. And they are seen in experiments, but I think there still lacks a full understanding of their stability and of the full set of models that can give scar behavior. So with this, I'm going to close. Thank you for your attention.
All right, thank you very much, Andrei. So now we have some questions that came in the chat, so I can read those, and then in the meantime, hopefully the option to raise your hand is available. So please go ahead and hit that option on the participants page, and then I should unmute you and you can address Andrei directly. So if we don't have any, okay, we do have someone. So
I can see some questions, right? Or maybe
yes.
Should I read them from the?
So someone just raised their hand and it went away. So could you do that again? I just want to be able to.
So there's some questions in the chat, so I can answer them while.
Yeah. So I'll go ahead and read them.
Yeah. So I can. Oh yeah.
Okay. So Daniel, you can go ahead and give your question.
Did you hear me?
Yes.
Do you hear me?
Mm-hmm.
Okay. This example of Hubbard model, can it be this SU4 effectively? Can it be represented in form of Dirac gamma matrices 4x4? And how would it look like in this case, in this representation?
Right. So SO4 has right? So it's SO, what is SO5 mod S5. So I guess has 6 generators, right? So I think, I'm not sure that it can, so Dirac gamma matrices, there's 5 of them, right? So I'm not sure if you can, I don't think you can represent them purely in terms of Dirac gamma matrices, as far as I think, right? There's 6, SO4, there's 6 generators, right? You can't, right, because it's SE2 cross SE2, and there's a Z2 also. So basically, so I'm not sure if you can represent them in, right? There's 5 Dirac matrices. I don't think, I bet they, you know, like they haven't, there's, so one of them, is this, let's just get to, one of them is the spin, which is just C dagger sigma. So it's C dagger sigma dot C, okay? So and one of them is, you know, this right, C dagger sigma X C dagger, right? So you can see it here. So it's C dagger sigma X C dagger, and one of them is the spin is C dagger sigma C. So I could represent them in a basis that contains both C and C dagger, because one of them is charge 2, the other one is charge 0. So I could represent them as sigma cross tau, right? So think of the eta pairing as being some tau x here. So I could represent them as sigma times tau, but I don't think those would form a basis which is not exactly the 5 Dirac matrices. So I could represent them as, you know, as a tensor product of sigma times tau in a C dagger basis. Does that answer your question?
Yeah, okay.
Thank you. Thank you.
All right, Jose, go ahead. We should be able to hear you now, I think. Yes.
Yeah. Hi, Andrei.
Hi.
Thanks for the nice talk.
Thank you.
Can you hear me?
Yes, thank you.
Yeah. So what are the implications when you put in some disorder? I'm worried about the many-body localized state. Can we say that this kind of system would naturally evolve into a many-body localized state when I put in some disorder in the
Yes,
system?
that's a very good question. So it's not entirely clear what happens to these cars once you add disorder, right? So it's not, so right now these states, even though they're in the middle of the spectrum, they're completely decoupled from the spectrum, right? So they're kind of like, they sit around, they have their entanglement entropy, which is being log of a volume, and all the other states around them have volume law entanglement entropy. But they kind of like, even though they sit in a huge density of states, like exponential density of states, they kind of don't talk to them. They're very, so they won't thermalize. Now, when I add disorder, you know, the ideal thing that I'd like to say that I cannot say is that they're still stable to disorder, to some disorder, or to some disorder configurations. But I can't, I don't, you know, I would like to be able to say that, but I have no evidence for that. Especially the problem with adding disorder is that you lose every analytic tractability that you have. Yep. So then you have to go back to doing numerics and scaling, and then, you know, it's, yeah, so and then you're at the mercy of your scaling working, or, you know, your numerics actually being you know, being correct in the thermodynamic limit. So that's a good question that I don't have the answer to. I would hope that there's still some disorder configurations for which these states survive.
All right, thank you.
But you know, survive meaning, yeah. So in this case, the log L, the entanglement entropy, disorder states would move from volume, if they're many-body localized, disorder states would move from volume to area law, which would be constant here, because I'm in one dimension saying the equality. I would like to think that these scarce states will still have log L, so nothing. It would be, yeah, but I don't have any proof of it.
All right, thank you.
Thank you.
Okay, Eris, you should be able to unmute yourself, I think.
Hey, Andrei.
Hi.
Hey, is it log volume or is it log volume of subsystem?
So first of all, you're right. It's log volume of a subsystem, but usually you keep the subsystem half of the system. Normally, that so you take right. So you take so basically you integrate out the system. So it's it's the log volume of the subsystem.
But you don't have to take half. Right?
Well, you don't have to take yeah, but you take you take a finite. Everything goes to infinity in the end, right? So you take what you can do. The right way to do it is you first take L to infinity, and then you take out an infinite subsystem of that. But in any case, it's log vol. It's going to be log volume. Basically, it's log volume to get to the middle of the highest part of the spectrum is volume. So the bandwidth is volume of this. The way, of course, I can make the bandwidth finite by just dividing the Hamiltonian by the volume, but I didn't. So the bandwidth is volume. So the state that goes into the middle of the spectrum, its quantum number is going to be volume over 4. Okay, volume over 4, and that state will, it has bond dimension. It has bond dimension log of volume over 4. So I guess it's volume. So it's actually the volume of the full system in this case. Actually, you're right. So it's the volume of the full system because that state is the volume over 4. It's got bond dimension less than volume over 4, so you can prove that it's less than log of volume over 4. Mm-hmm. And your other question that I see in chat, you're certainly right. There's an even-odd effect, as you pointed out in the chat. There's an even-odd effect. These states are therefore even-odd for even L, even-odd. They're there for even L.
Are you saying that scars don't exist for odd L? Or?
No, I'm saying you can build. I'm saying this. I'm saying that there's a difference between scars and exact scars. I mean, there's a difference. There's no difference physically, but the difference is exact scars. You can find an exact expression for the states. Okay, mm-hmm. And the exact expression is not there for odd L, but if you solve it, you're going to see.
And so the integer energies are always even, but the rational energies always involve odd coefficients.
I'm not sure if the irrational energy. That's a good question. I'm not sure if the rational energies involve. I would think. Yeah. I'm not sure because there's still momentum pi, which is kind of hard to get on an odd L. Like all these states A and B, I didn't write them down. There's still a momentum pi. See. Mm-hmm. These states vary between pi and 0. You see, yeah. So they're probably everything here is for even, probably. I guess there's some states. Sanjay and Nicolaus, there's some states for odd, but I don't know which ones they are. But basically, these are all pi's here. You see, the S goes from pi to 0 to pi to 0. So all of these are for even. All right. Their exactness is for even, right? But if I go for odd, I would see some other. Right? I would see there'd be low entanglement states that wouldn't be exact, like in the PXP.
Okay, got it. Thanks.
Thank you.
Okay. All right, just a quick announcement. So normally we have these talks every Wednesday, but we sometimes have them on Monday. And so next week we actually have a talk on Monday. Just to let everybody know, it's the same time. We'll obviously send out an announcement as well beforehand on Sunday evening. So do we have any more questions from the audience? I think Isaac. All right.
There were some other questions on this group chat, but
yes. So we'll do the voice question or the audience questions, and then I'll go through the chat.
I see.
Okay, can you listen to me?
Yes, I can hear you, Isaac.
Yeah, thanks for it was a very, very nice talk. I have a couple of questions actually. So the first one is related to a previous question somebody asked you about when you put disorder in the system where you expect to go to localized to delocalized states, whether it would be possible to have something in between, like mixed states, that instead of going to volume to area law, you go to something in between, whether that's a possibility. So that's my first question. And my second question is, like, in certain ensembles of random matrices, it is known that, for instance, if you look at the spectrum, you may have a continuum spectrum, and then you may have localized states in between the spectrum. I was wondering if there is some connection with something you mentioned before, that you were studying some extension of your work in random graphs.
Right. So to be honest, I'm not so related to the first question. So I don't know the answer. So I don't know if there's so. Normally, I would think you're right. I would think I could add some disorder and go from volume to area to MBL localized. But I don't remember the generic behavior. Maybe somebody else knows it in MBL. I don't remember if you with infinitesimal disorder and then adding. I don't remember if you've got. I guess if you've got the mobility edge, you should probably go to area law and then localize. But I don't know. And right, the second question. Sorry, the second question was related to graphs.
Yes, you mentioned something that there was something written somewhere, something about random graphs or some of random graphs.
So you can. So that's very good. Thank you. So you can actually generate this Haber model on. I think it was here. You can generalize the Haber model on arbitrary graphs and with disorder and spin-orbit coupling. So what happens is that, not generalize the Haber model because that's obvious, but generalize the eta pairing. And you can add spin-orbit coupling and disorder. And if the interaction, there's some constraints on the interaction and kinetic terms with disorder and spin-orbit coupling, and you can still have this eta pairing. Okay, and then as you pointed out, then with this type of disorder, so this actually related. Very good. Thank you for asking this question, because now I can actually more properly answer Carlos's question also. So on these graphs with this type of disorder and spin-orbit coupling, this eta pairing state that we've created here will still remain an exact scarce, right? So, but there's two caveats to this. First of all, even without disorder, the interaction that you need to add to have, so the eta pairing states by themselves, or the C and Yang eta pairing, will die the moment you add a generic other interaction on top of the Hubbard. So next nearest neighbor, for example, or some second hopping. Okay, so that's the first thing. So you need to add a specific interaction even for the order model in order to still have some eta pairing states remain. And these are the scarce states. So this will stop making the eta pairing the symmetry. You add some specific interaction with this specific form, and these will remain scarce. Now, furthermore, what you can do, and this is related to what you just asked and what Carlos asked, is I can generalize this model on graphs with disorder and spin-orbit coupling, and then still have that eta pairing, those states, when I add this extra interaction, be scarce. So if I generalize the Haber model on arbitrary graphs with disorder and spin-orbit coupling, I can have the full eta pairing symmetry. Then I add the extra term, and I can still have them remain scarce. Just some of the eta pairing states, I can have them remain scarce. Now the issue is that these disordered spin-orbit coupling, in order for this eta pairing to remain a symmetry, it's a very contrived disorder. You know, they have to satisfy, like disorder between two sites has to satisfy a ratio with the hopping between two sites.
Mm-hmm.
You know, so it's not entirely clear. It's not uncorrelated disorder. Right?
Okay. Thank you.
So the generic situation is certainly not clear, but you're right. And, you're right. The statement does say that we can do that for a set of disorder, but it's just very contrived. Thank you.
Thank you.
Okay, so there are some questions. I can say them, but it looks like they were answered, but I think they're interesting questions either way. So this one from Nancy says, is the implication that the existence of these states, the fact that there are states in the middle of the spectrum that are like islands that show no correlation with the rest of the states, I'm assuming, when they're within the same energy range? And I think that's kind of what your talk implies.
Yes, exactly. That's exactly what they are. Yeah. And moreover, it's like the spectrum is exponentially dense around them. There's an exponential number of states around them because the density, the energy density in the middle of the spectrum is exponential. So there's a lot of them. So, but yeah, that's exactly what they are, like Nancy said.
Now, do these actually, one question I have is, so in ETH, typically the expectation value of local operators is usually like extremely diagonal in the eigenstate basis. Are these states similar in the sense that, like, if I look at a local operator, do they have very little overlap with neighboring eigenstates, or actually do they connect very well with the neighboring eigenstates via a local operator?
They have, I think, in these states are very low.
Okay, so they kind of act like an ETH state in the sense that, you know, they have very little. Okay, the matrix elements are still basically diagonal.
Yeah,
the eigenbasis. Okay.
Yes, exactly. In that sense, yeah.
And then we have another question, which is about whether or not this can be extended to higher dimensions, and of course, yes. Okay.
The Hubbard model, yeah, it's not entirely clear for the spin models. I think Yadekola had, yeah. So like I think there's some papers which this one was the spin one XY model, but they also them and I think Alexei Motronich. And Lin.
Yeah, I think the PXP is also higher dimensional. Yeah,
exactly. They were able to get the PXP to higher dimension. They were able to find, so the PXP has a set of zero energy states, which is exponential, and they were able to find two of those states actually in the PXP model in 2 dimensions of the set of exponential states analytically. But it's somehow it's harder for spin systems than for the Hubbard model. Seems to like just follow through. But for spin systems, there are generalizations. It's just not that many, I think.
Okay.
I think that would be kind of a good, yeah, if we can kind of come up with a constructive way of doing them in 2 dimensions or 3 dimensions.
Yeah, is there any obvious way you could extend it to like infinite U limit, where you kind of do a, because that's one way of.
Yeah, when you do it. Yeah, that's a very good question. So I don't know if even eta pairing survives in that limit.
Okay.
You know, after the TJ transformation, it's a very good question. Yeah, I don't know. So
one interesting.
I don't know whether the eta pairing survives in that limit, and I don't think it does. Just well.
One thing to note is that the PXP model is actually kind of like this infinite. It's like an infinite U limit, but you can derive at least the 2D PXP model. You can derive as an infinite, or basically very small perturbative transverse field Ising model with a very large antiferromagnetic. It's like antiferromagnetic Ising plus longitudinal field plus a transverse field. And it's when the transverse field's very
Z2
small.
degrees of freedom plus antiferromagnetic plus Z2 degrees of freedom with antiferromagnetic coupling plus an Ising field plus.
Yes, very, very small Ising field. So it's the fluctuations that you get are basically a frozen, when you have a checkerboard pattern that's kind of nearly frozen, but with small quantum fluctuation. So it's conceivable that that could happen in the case of the Hubbard model, I guess. It's just,
right.
I don't know. All right. Well, thank you very much for this very interesting talk. And oh, actually, no, we have another question. Sorry. I'm going to unmute you, Musad. All right, you should be able to talk now.
Hi, Andrei.
Hi.
In the AKLT,
Yes.
if you have open boundary conditions, right?
Yes.
Does your construction, some version of your construction work? I guess you could take the odd reflection, and that would probably still be an eigenstate. So the nice thing would be that you would get not log n, but really order n to the 0, order 1 entanglement. Right? Because
I think you're right. So it's a very good question. So I think so with log with open boundary conditions, it certainly still works, the construction. But I think even if I take with open boundary conditions and cut half of the system, you'll still have log L, right? Plus some.
No, because you don't need to make this sum to make a pi eigenstate, right? Your eigenstate is probably just reflection, odd reflection. So your log n comes because there are n terms in this.
You're saying I don't need to take the sum; I can just do one of them.
Right. I think
let me. I don't know. I'd have to go through it, but like the issue is that the scattering of the Hamiltonian does push you away, right? So if I just take, let's see, you want to take. Right. The problem is, how do you get rid of this plus? Right. So I see. So you're saying you want. Okay, this is interesting. I have to see if there's a way to get rid of this plus, right? Because the -1 will get rid of it by just pushing it away in this case. But how do I get? You want to form. Right. What you want is to form a linear combination of some inversion operator that will cancel that.
Right. Just this plus its reflection symmetry, or this minus. I don't know which one.
Yeah. If I had. Yeah, it's a good. Yeah, that's a good point. I have to see. We did solve the system for open boundary conditions, and I don't remember the result actually. If there were more eigenstates, you see, because you see these immediately in finite size, right? The problem is that I really think I need a sum, because otherwise they'll just, But with open boundary conditions, it's maybe there's a little bit of a different mechanism. I don't know. That's a good point. We'll try that.
Thanks.
Thank you.
All right, so Isaac, you have another question?
Yeah, sorry. Yes, can you listen to me? Yes, all right.
Yep.
Yes, one more question. In the model where you have the tower states, if I understood correctly, you have just one state, not per energy. That's
well,
right?
they're a spin multiplet.
Yeah. So
up to SU2 symmetry, you have one.
Yeah.
There's a full SU2 symmetry.
Yeah. So my question is, would it be possible to generalize the model so that you have degeneracy in these tower states? The reason I'm asking this, I'm suggesting this, or I'm asking this is then it would be nice perhaps to see when you have this degeneracy in these tower states, and you introduce maybe some disorder where how this thing breaks. And then maybe you go again back from area law to volume law.
So here, so you see here, right? So here I have so for example, the state that in the middle of the spectrum is a state that say L/2 or whatever, right? Like this state, say so, or some as I go to large. So this has a spin 8, for example. So the spin also grows. So the degeneracy, and it's a full 2s+1 multiplet. So you do have the SU2 spin degeneracy. Now you can break that, I guess, with, for example, like this. So this Hamiltonian, which still has the same set of scars. This one doesn't maintain SZ symmetry. Okay, so this one will have, it's kind of like, so the AKLT has an SU2, well, this one has a Z symmetry, doesn't have SU2 symmetry. The AKLT has a full SU2, so each of those spin 2 states of the spin 2 operator, if I had the spin 2 operator many times, I'll have a high spin state. Each of that has this SU2 degeneracy, a 2s+1 degeneracy. Now I can break that and keep SZ symmetry and still have the same set of scars, which is S plus and momentum pi on the ground state. All the other sets of the multiplet have gone away from this, but I don't know what would happen with disorder. So what I know for sure is I can break SU2 symmetry and have these degenerate multiplet of scars break into one scar, which is S plus, because this Hamiltonian doesn't keep, say, SE2 for generic ZJ. Okay, for generic numbers ZJ, I could have just S plus squared momentum pi on the ground state acted however many times, and those would be the scars, but not the full multiplet. But I don't know what would happen to disorder. So I could certainly break the degeneracy of the multiplet of scars at each energy and still have scars remain if I add this is the translation invariant perturbations to the Hamiltonian, but I don't know what happened to the scar if I add disorder. Like SU2, for example, break-in disorder. Is that sort of what you were thinking about?
Yeah. Thank you.
Okay, thank you. Thank you.
You're muted.
Of course, I'm muted. All right. If there are no more questions, I'd like to thank you, Andrei. It was a wonderful talk. And I hope to see everybody next week on Monday for our talk. I don't know who the speaker is yet, but you'll get a reminder on Sunday evening and on Monday, hopefully. All right. Thank you very much, everybody. I hope you have a wonderful day.
Thank you.
Yeah.
Thank you very much. Bye.